professionalism, CAP has played a leadership role in bringing together different natural scientist organizations. It was the catalyst who brought together all those organizations to lobby under the natural scientists lobby to stand up towards the encroaching role of engineering associations across the country were pressuring governments to set up laws defining the domain of professional engineers as basically encompassing every human activity on the surface of the earth. And we have very successfully resisted those changes in different parliaments from British Columbia, Alberta, Quebec, and the Maritimes, and Ontario also. The second role of the CAP has been to serve as the main lobby group of science and physics in Parliament. On Parliament, it's a continuing role of public policy, and also promoting physics profile in terms of granting agencies like NSERC, was now regularly going through reallocation exercising, reallocating the money as given to science for research. And the physics has been rather disorganized at the beginning. We each did our own little thing, particle physicists, general physics, condensed matter. Physics is very broad and covers a lot of disciplines, and there wasn't this cohesiveness that you would find in particular, for instance, in the Chemical Institute of Canada. And but this has changed a lot over the last few years, and the Canadian Association of Physicists has served as the basic catalyst for this lobby group. The CAP offices are right here on campus in this building down the hall. So if you wish to register, there are free membership for students first time through, which includes also a membership to the American Physical Society. So it's a good way to get into the profession. And student fees are fairly low. Now this is...
Stop.
I should stop?
No, keep going.
I keep going.
Can I get some...
What do you need?
I need someone to help me with this tape.
He needs a technician.
Real life, folks?
Yes, and here you see Steve Morris, who is preparing for us a rather major demonstration, including all kinds of the latest technologies in lecture giving, including some real-time demonstrations. Steve Morris, I've known Steve Morris for many years. Steve did his getting cut on the rope here. Undergraduate at UBC, and his graduate at UBC too. He's a professor now and at the University of Toronto. He's always been a very lively promoter, all talking, nonlinear dynamics. And his webpage has plenty of pretty pictures about the kind of things that can happen in fluids and in highly viscous materials. He has a number of collaborators, including one of his brother-in-law, actually, would you believe it? John de Bruyn from University of Memorial University. Now, today he'll talk about the whole issues of order from instability, nonlinear patterns in nature and the laboratory. Now, Steve, I don't know if I should enter into a whole new subject line of discussion.
No,
we couldn't get this room before 2:20, so he requested half an hour to set up to do his setup, but I was afraid, there's no way I could.
in record time.
I actually even upset the previous teacher from this class here.
You're going to get chewed out.
I got chewed up in my office.
I didn't have to mind the lie for you, so.
Sorry?
She asked me what your name was, so I had to practice.
Anyway, I did all my apologies. I could tell her that it was not something personal against her.
Okay.
So, Steve, the floor is yours.
Thank you for the introduction.
Fine.
Right. Well, I'm going to attempt something that only a crazy person would do. I'm going to attempt 2 demonstrations. Count them, 2. And this is for 2 reasons. First of all, it's fun to try and make real life actually happen in the classroom. When you do this kind of thing, you realize how different it is just to give a lecture than it is to actually do something real. So it's kind of fun to try and do something real for a change. And the second reason is to show you something, to demonstrate to you something that I think is a fascinating aspect of the field that I'm going to tell you about, which is the fact that you can do state-of-the-art experiments, which are forefront science, which you can carry with you in the trunk of your car. And here's one right here. And there, with some caveats, is another one over there. So if you're under the impression that physics requires accelerators of hundreds of kilometers circumference and similar large facilities, you are incorrect. You can, by going to your local junk shop and putting together bits, and with a little bit of high tech, which I'll show you, you can do very interesting, very state-of-the-art experiments. And that's part of the subtext for bringing these things to you, to show you that that's possible. Okay, so the subject I'm going to talk about is, roughly speaking, nonlinear physics. And I give it the title Order from Instability, and that's supposed to sound like a kind of contradiction to you. Normally, if I said instability to you, this would be a bad thing. And instability tends to make things that are ordered fall apart, or in general, you don't expect order to come from something that's unstable. But I shall argue to you that, in fact, most of the order that you see around you in the natural world is actually the result of one instability or another. The working out of systems that are actually quite unstable. And the subtitle is Nonlinear Patterns of Nature in the Laboratory. Now, I brought some of the laboratory here, but I'm sorry I didn't bring too much of nature with me. But I do have one picture. And I should say this is the work of many people. I didn't list all the people on the front page. I'll try to remember to tell you who they are, my students and collaborators, as I go along. I did bring one nature picture, which is a famous one, taken by Ansel Adams, who is a famous California photographer. And it shows the ripples on a piece of wind-blown sand. It's actually a sand dune, and those ripples are maybe 15 centimeters apart from each other. And the wizardry of Ansel Adams is that you can see the distant ripples, and you can see the foreground ripples, and if you look closely, you can see the grain. You can see the shadows of the grain. And supposedly Ansel Adams tilted the plane of the plate in the camera in order to get the depth of focus from all the way from grain to the distant mountains. What I'll show you. The kind of tricks you play when you're a photographer. But the point is that this is an example of a regular structure that has appeared spontaneously out of something that you would have expected to produce complete disorder. If I comb this sand flat and I blow the wind across it, the sand all jumps around in a complicated way, and you would not guess, if you had not already seen it, that after you turn the wind off, or the wind goes away, left behind would be this almost perfectly ordered regular stripe pattern. It's not perfectly ordered. There are a few little sort of characteristic defects in it, but generally the wavelength is remarkably constant, and the direction is remarkably constant. By the way, the wind blows across it this way. And under the wind, the pattern actually crawls. It moves along slowly. Although, of course, when the wind stops, it's static. So what are the ingredients? What do you need to get a pattern like this? Well, first of all, you do not need equilibrium. You do not set the sand down flat and then wait a long time, because it will not get to this state that way. You drive it. So this is an example of a pattern that is occurring in nature under driven, open conditions. And in fact, another important feature is that it's dissipated. In other words, it has friction. As the wind blows across it, the grains bounce around, they rub on each other, they dissipate some of the energy the wind is putting in, and it is the dissipation which, if you like, is the sink for the energy that the wind puts in. And the pattern emerges in a kind of non-equilibrium state which is suspended between the driving force and dissipation. And so the whole subject I'm going to tell you about are so-called dissipative structures, or structures that emerge under non-equilibrium driven conditions. And in fact, if in general terms you can think of just about every ordered pattern in the world, including this building and you and I, as being an example of one of these things. After all, we would disappear if we were put into equilibrium, right? Put you inside, put Bela in a box, and seal the box all up. Wait 10 million billion years, Bela will be a kind of thin gas in the box. He won't be nearly as interesting as in equilibrium today. But if you give him a good breakfast, and you give him, some room to bounce around in, sweat a bit maybe, then he's a much more interesting character. And that's kind of the moral of the story here, is that physicists spend a lot of time studying equilibrium structures, and they're very interesting. But in fact, most of the structures in the world are the result of non-equilibrium driven, unstable processes. So here's a kind of roadmap. They arise under non-equilibrium, that is to say, you don't close the box on a long time, you keep it open. They're driven, so there's energy flowing into the box and out of the box all the time. And these conditions are rather like the real world, and that's why these patterns occur a lot in the real world. So if I could contrast that equilibrium, you typically have a static distribution. It may be very ordered like a crystal, but it's characterized by the maximization of something, which is the entropy of that state. You know that if you close the box up a weight, it will maximize its entropy. And it always seeks the equilibrium condition. So if you're perturbed from it, it will always fall back to that equilibrium a little in a short time, in a very short time. In contrast, open systems, energy flows in and energy flows out. Now, of course, energy is conserved. It doesn't build up normally in these things, so the same amount flows in as flows out. But these are dynamic, dissipative systems, so that means entropy, in fact, is being continuously produced in these systems. Every time you rub something against something else, entropy is produced. Entropy is not conserved, as I hope you remember. So these systems actually produce entropy. You and I are constantly pouring entropy out into the world. Now, that allows us, paradoxically, that allows us to become more ordered. And it allows these non-equilibrium systems to become more ordered because they're open. They're open. We are connected, if you like, to the heat bath of this room. And this room is connected to the heat bath of the dark night sky. And ultimately, our organization, such as it is, I shouldn't say that in Ottawa, I suppose, but our organization is ultimately the result of the temperature difference between the surface of the sun and the 3-degree background radiation on the other side. Everything we do is driven by the energy which flows from one and leaves by the other direction. And we produce entropy the whole time. Okay, and get more and more ordered, hopefully, as time goes on. Okay, so there's no minimum here. These type of things can run downhill for as long as they like, because the hill is, in a sense, constantly being replenished. Okay, so if I take a driven system like that, and I start at an equilibrium, and I drive it fairly gently, then what usually happens is kind of boring. You get a uniform kind of flow state. But if you drive a little bit harder, typically the first thing that happens is the system becomes unstable in some way. And that instability begins to grow as some kind of spatial or temporal motion, and it will encounter the dissipation in the system and be forced to not reach some kind of infinite velocity by the driving force. It will reach some magnitude which is limited by the dissipation or by the friction. Okay, so here's the sort of cartoon scenario. You take a driven system, it's unstable, and it grows up to some size and saturates because of the nonlinearities in the problem. Okay, so you need a little picture of this. Here's my favorite sort of Jimi Hendrix example. I date myself here, I suppose. But if you take a stereo with a speaker and you attach a microphone to it, every kid has tried this. You hold the microphone up to the speaker, and first you hear nothing. You get a bit closer, and then it begins to howl. And then your parents begin to howl, right? But anyway, why does that happen? Well, why doesn't it howl at infinite magnitude? Well, it's because you've turned it up to 11, but 11 is not infinity, and the amplifier can only go so far. So what happens is it runs up until it becomes nonlinear. Okay, until all the energy that's going in is dissipated as hard as it can against the dissipation, and the magnitude has reached the maximum. Now, more subtly, why does it howl at a particular note? Or roughly a particular note? Well, it turns out that many instabilities are neither of, they produce some kind of structure which is neither of infinite wavelength nor of zero wavelength, but is something in between. Like those sand ripples, for example. As long as the wind blows, it excites the sand, but there's one wavelength, roughly, which happens to be the one that is preferred by the system. And so that's my cartoon here. Those are called pattern-forming instabilities. Now, it can be either in space or in time, or in general in both. Now, typically, if you push harder, if you keep on increasing the driving force, then you get to the sort of thing you might have expected, which is some kind of really messy, turbulent state. Okay, but I'm not going to talk about turbulence today. In fact, turbulence is a very hard problem for that reason, but I'm going to talk about systems where you drive just gently enough to get past the first instability or two, and then no more, and you just look at what happens there. Okay, and there are many natural examples of that. The example that's been studied in great detail, which I'll show you a lot of pictures of, is thermal convection. Now, this is a little hard to demonstrate, so I didn't bring this demonstration. But what it is the following. You take two plates, and you put a fluid in between them, and you heat the bottom one, you cool the top one. And the temperature difference across those two plates is the non-equilibrium parameter that I've been talking about. The higher that temperature difference, the harder you're driving the fluid. So what's happening? Well, the bottom is hot, and the hot fluid thermally expands and wants to rise, and the cold fluid at the top wants to fall. So if there were no viscosity, it would just begin merrily overturning and carrying the heat convectively like this. But because there's some viscosity of the fluid, it doesn't do that immediately. And so in fact, you have to reach a critical value of the temperature difference, which depends in a funny way on the height of the cell, before the fluid will begin to convect. But when it starts convecting, it develops a set of sort of jelly rolls like this, and those are the pattern that I'm talking about, and they have a particular characteristic wavelength. Now, when you do the theory of this, you can do a linear theory of this fairly easily, and Lord Rayleigh did this around 1916. You do is you calculate, you ask, if I perturb the fluid at some wave vector k, which is 2 pi divided by a wavelength, and I ask, does the motion that I put in there tend to grow as a result of the forces or decay? And I do that as a function of this funny dimensionless number called the Rayleigh number, which is proportional to the temperature difference. So it depends on g, the acceleration to the gravity, alpha, the thermal expansion coefficient, the cube of the height of the cell, the viscosity of the fluid, and the thermal diffusivity, or if you like, the thermal conductivity of the fluid, times the temperature difference. As I increase that number, the temperature difference becomes larger and larger, say. I reach an instability. So what happens, what you find is that in this plane of r versus k, there's this funny U-shaped curve. Everything above that curve is unstable. Everything below it is stable in the sense that it will not start convecting. So as you increase the temperature difference, what happens is you move up here, and you bang into the nose of that curve. So the fluid becomes unstable neither at a very long wavelength nor a very short one, but at some wavelength in between. And then that is the wavelength roughly of the convection rolls that you see. And I'm going to show you a picture of them in a minute. And once you get inside of this nose here, it's game over. Linear analysis no longer works, and very complicated things happen, as I will show you. So what happens if you look at the flow velocity is you get what's called a pitchfork or a forward bifurcation or branching of solutions as you increase this parameter epsilon, which is just whether you're at the onset of convection or not. If it's negative, you get no convection, you hit 0, and the convection starts to grow, and it turns out that it grows from 0, like a parabola. Okay, that's called a forward bifurcation, very complicated. Okay, well, suppose we did this experiment. I've done this experiment. I'll show you the data in a second, but how do you see the convection? Well, it's a very nice experiment because there's a very clean way to see the convection. If you shine a parallel beam of light through a convecting fluid, here's the convecting fluid layer down here, and the warm areas have a slightly smaller index of refraction than the cold areas because of thermal expansion. And each little convection roll pair, there's a warm one and a cold one, a warm, cold, each one acts like a little lens and concentrates the light a little bit. Now in practice what you do is you make the top of the cell out of sapphire, which is transparent, and the bottom a mirror, and you just bounce a beam of light through it. And you land that on a CCD camera, and you take a picture with the computer, and then you analyze it with the computer. That's how you do this experiment. Now the pictures I'm going to show you are actually used carbon dioxide gas as the fluid, and there are technical reasons why carbon dioxide gas is a good choice. And as long as the height of the cell is not too high, then it turns out that the temperature difference required to get convection is not very big. It's only a few degrees in this particular experiment. Okay, what do you see? As soon as you go through the onset, first of all, you see nothing, right? And you increase the temperature difference, and it begins to convect. Now you're looking down on the cell, and each of those little white lines there is a cold downflow. And each of the black lines in that picture is a warm upflow. So you see spontaneously out of no structure has emerged a perfectly ordered stripe pattern like this. And it breaks the symmetry of the cell. The cell's round, the pattern comes up in any orientation. Every time you do the experiment, it comes up differently. Okay, so that's a nice example of a very clean nonlinear pattern. And of course it stops growing, the amplitude stops growing because of the nonlinearity in the cell. Well, that's interesting, but not surprising. That's what we would have guessed. But what is interesting is what happens when you increase the temperature difference farther. Remember I told you complicated things happen, so let me show you what they are. First of all, the rolls no longer wish to be straight. They start to bend. And in fact, they bend partly because they like to be perpendicular to the side walls of the cell. They also form little defects. This is called a zipper, and this is called a focus singularity. And as you increase the temperature still further, it was expected, when we did this experiment, it was roughly expected to see more of this. But in fact, we saw something new. You see spirals appear. Here's one, here's another one. And they begin to wind, and they wind, and they wind. And as you go a little bit farther, you get a new state which is not static, which is thoroughly dynamic, which is in fact an example of a spatio-temporally chaotic state. And now I will show you what that state looks like in time with the touch of a button, right? I have to turn this off. Okay, this is speeded up about 50 times over real time. That's not very much speed up. And you see the spirals wind up and crash into each other. It looks kind of like a boiling plate of spaghetti. Now, it's important to emphasize that it looks thoroughly random, this state. But in fact, it's extremely ordered. There's only one wavelength in this problem. The spacing of these rolls is very close to being a constant in this experiment. The only thing that's moving around is whether they're spirals or other kinds of defects that are being created and destroyed.
There's still only one layer roll?
That's right. We're only about 50% over the onset of convection here. So the temperature difference is much too small to produce turbulence. All the flow of this experiment is laminar. Okay, I speeded up the video. All the flow of the experiment is completely laminar. If you were in a little submarine, going around, you would just experience a kind of simple flow, which was kind of dull. Okay, well, that's an example of a spatio-temporally chaotic state, and it's in fact deterministic. There is absolutely nothing random about that pattern. If you give me any frame of that movie, in principle, I can predict all frames into the future. Now, in practice, it's exponentially more difficult to do that because small errors in the initial conditions grow exponentially. So it's rather, if you know anything about chaos, that is the characteristics of chaotic motion. Okay, so that's an example of a spatially and temporally chaotic pattern. Let me show you some more regular patterns. I mentioned that if you make the cell large, the temperature difference is small, and you can get to a different limit by making the cell rather small, and then it turns out that the temperature difference to get convection becomes large. And the fluid problem becomes different because if the temperature difference is large, then the viscosity, say, of the fluid, it can be quite different at different temperatures. So you can no longer neglect the temperature dependence, say, of the fluid viscosity, which you could in the previous case. And when you do this experiment, you discover a completely different set of phenomena, or somewhat different set of phenomena. First of all, the onset of convection is backwards. In other words, it jumps in a step to a pattern rather than smoothly. And the pattern that it jumps to looks roughly like this, a little donut-shaped convection roll. And so here's the onset of convection in a cell like that. You get a little patch of hexagonal flow cells like this, which then grows like a crystal until it fills the whole cell. Here it is filling the whole cell. Okay, it looks like a crystal or something, but in fact, each of those little things is a little, donut of convection flow. If you turn off the temperature difference, it goes away. Now here, the temperature difference, by the way, was about 30 degrees, so that's a pretty big temperature difference. Okay, well, remember our golden rule is if it's boring when the parameter is small, just keep turning it up, see what happens, right? This is the sort of, methodology of the field. Keep going until you don't understand anything, and then, when the theorists understand that one, you just turn the knob another notch and they don't understand that one. So here's what happens now. This is a bit of a shocker, I warn you. What happens when you keep increasing? Well, what was predicted? What was predicted was that this hexagon pattern should go back to the straight roll pattern. There should be a transition to rolls. Well, here's what was seen. And this, by the way, was done by Eberhard Bodenschatz at the University of California at Santa Barbara. First of all, you begin to see a little defect around the outside. And then they begin to grow some rolls. So you see over here, there's some stripes appearing. And as you keep going, the stripes and the hexagons start having a war. And they fight back and forth, and they fight back and forth, and there's a little salient here and a little, field of rolls here. And you keep going, and eventually you get all rolls. Let me just show one more. This was pretty much all rolls. There's still a little hexagon hanging on there. But then, believe it or not, what you get is this. Okay, that is in fact a steady, rotating spiral pattern. And it rotates about every 30 minutes or so. Now, the time it takes for a parcel of fluid to turn over in a convection cell is only about a second. So that tells you this is a very slow motion compared to the fluid motion. Now, this is a little hard to look at.
Sorry, what changes in 33 minutes?
A complete rotation of the spiral. Well, let me show you the next picture. In fact, it's a spiral, a two-arc spiral defect with two disclinations here and here. And these orbit the center once in 33 minutes.
So the defect orbit, or you think the whole thing is orbiting?
Well, the outside part is concentric, so it doesn't orbit, but the inside part rotates around and this winds up. It's like the spiral would keep winding up, so it's got to get rid of those rolls somewhere, and they're eaten continuously by this defect. Okay, so instead of a steady state, what we found is what was found was a non-steady rotating spiral state. Okay, well, in an attempt to understand the difference between this experiment and the last one, we performed the following experiment. It turns out, you may have noticed that the spiral meant the sidewalls parallel rather than perpendicular. Why is that? Well, in that experiment, the sidewalls were built out of a ceramic material, whereas the previous experiment was built out of a material which had less thermal conductivity than a ceramic. So we suspected that, in fact, it was the thermal conductivity of the sidewall of the cell was leaving a little temperature gradient there, which was doing the job. So we built a cell which had a heater in it. Okay, if you can't make an effect go away, then turn it up, right? That's the important thing to do. Okay, so we turn on the heater, and you see, this is even below the onset of convection, you see that there's a little roll all the way around the outside of the cell. And then I can turn it off, and I get back to the previous conditions. Okay, so here's what it looks like with the heater off. It looks like the sort of fingerprinty thing that I showed you before. If I do nothing except click on the heater and wait for a while, I get a spiral. It's not quite the same number of arms, but it's a spiral. But you'll be happy to know if I increase the heater a bit more on this pattern or on any of these patterns, I get back spiral defect chaos again. Okay, well, what about hexagons? Okay, well, hexagons are actually seen in other kinds of convection. The one that you may be familiar with is Marangoni convection. This happens in a frying pan all the time. If you heat a fluid from below, but you don't put a top plate on, you just let the top surface be free, it turns out that gradients of the surface tension on the top surface can drive flow. And that gives you hexagonal flow patterns. So here's the mechanism of the instability up here. If I heat the fluid from below, and I imagine a little warm spot on the free surface up here, then what happens is the surface tension goes down on that spot because the temperature derivative of the surface tension is negative. Heat the fluid up, the surface tension goes down. So that place has lower surface tension than the surroundings. So the surroundings haul fluid away from that place. And that causes an upflow which hauls fluid from below, which is warm. Okay, so that warm fluid rising warms up that place that was already warm, and that's an unstable situation. It turns out that if the layer is very thin, this mechanism dominates over the buoyancy mechanism that I told you about a minute ago. In other words, the amount the fluid is lighter as a result of thermal expansion is negligible if the fluid is thin. And so, if you make a very thin layer of fluid with a free surface and turn on and heat it from below, this is some experiments done in Texas by Harry Swinnington and Mike Schatz et al., you get indeed a hexagonal flow pattern. Now this mechanism is totally different than the one I mentioned a little while ago. So this is another important thing. Just because you see the same pattern doesn't mean that the physics is the same. The physics is totally different. But you get a hexagonal flow pattern. Now the reason I'm showing you this is to give you an excuse to see the next pattern. What happens if you, turn it up? Turn it up. Okay, what happens if you turn it up? Well, it goes into squares. This was a complete surprise. Even though this instability has been studied for almost 100 years, it turns out that if you do the experiment carefully and use a modern fluid instead of whale oil, like was used in the original experiment, you find, in fact, that the flow pattern is a transition from hexagonal flow to squares. Okay, so now I've shown you, let's see, stripes, spirals, hexagons, squares, and spiral chaos. All right, well, one more. Now, the problem with the previous experiment is that you heat the fluid from below, you have a free surface, but you always have air. You always have air above the free surface. You have to have the air there because the heat has to go somewhere as it goes through the free surface. You're heating from below, you have to take the heat away from above somehow. So, in fact, you can't control what the air is doing in the experiment very well. You can't see it and so on. So we decided to do an experiment in which there were two fluids. Top fluid is water, and the bottom fluid is a fluorinated hydrocarbon called FC75. Don't worry about what it's made of. In fact, I'm not even sure what it's made of. And the point is that now we're going to heat from below a double layer of fluid. And the conditions are such that we have an instability which should be very similar to the Marangoni or surface tension-driven instability that I showed you a minute ago. It's just that now it's the interfacial surface between two fluids that sits there, and not the free surface, not the air fluid. Okay, so you turn it on, We know exactly what wavelength we expect because that, as I showed you at the beginning, is a linear problem. That problem's been solved a long time ago. The only question is, what shape is the convection cell going to be? Anybody care to guess? Any guesses? Hexagon?
More.
That's what we thought. We expected hexagons. No one has ever done the experiment before. We did the experiment, and what do you know? Squares. Okay, so these things meet at 90 degrees, and so they're squares. Now, what happens when you turn it up? Well, you turn it up, and it makes a transition to rolls. So there's partway through the transition. You go a bit farther, and the rolls eat up the squares, and you don't get a big spiral. You get a kind of fingerprinty thing that you go for. By the way, the difference between this pattern and the pattern that I showed you with the many, many rolls in it is just the height of the cell. It turns out for gases, you can make the cell very small height. In this experiment, you can only make the cell a few millimeters high, so the rolls actually scale with the height of the fluid, so these rolls are bigger. Okay, so now I've shown you that you can get squares at the onset of convection. Okay, now this would all be kind of fun if it was only concerned with convection, but in fact, the patterns that I've showed you, can I get the lights up for a second? Oh, I'll just turn on my little light here. Okay, I'm going to go to the video. I'm going to go to this video. Yeah, turn on that camera. Now, the patterns that I've showed you are all characteristic of convection patterns, and this subject would be a subject called convection if it weren't for the fact that you keep seeing these patterns wherever you go. Any instability, or many instabilities that prefer one wavelength over another, produce the same zoo of patterns. So what I'm going to do now is, hopefully, demonstrate for you an experiment, which I can actually bring with me, of a completely different instability, totally unrelated to the convection, which nevertheless produces a whole zoo of patterns which look very similar to the ones I've just showed you. Okay, excellent. So let me set it up here, and then I'll start talking again. This is a very expensive fluid. It comes from the drinking fountain. Okay, now we immediately have a problem. You should be able to see the light bulb in there. Okay, I should be able to see okay with that. All right, that'll do. Well, we'll try. Maybe the root, you can root the whole thing. Actually, let's do it.
What do you need? You need more direct light?
I just want to see the light bulb. There's the light bulb. Okay, that's the light bulb reflecting in the surface of the fluid. Okay, what it is, it's a puddle of fluid, and the thing it's sitting on is a powerful electromagnetic shaking device. It's like a speaker, only much more powerful. In fact, it can throw 50 Gs. It can throw a pound 50 Gs. And it's made by a company called Vibration Test Systems, and it's sold to people who want to shake the heck out of things to see if they break. Okay, that's what its commercial use is. Okay, so what I'm going to do is I'm going to turn on this ridiculously powerful amplifier over here. Stand back, everyone. Okay, that's a kilohertz. What we want is a considerably lower frequency than that. Okay, 100 hertz ought to do. So what I'm going to do is I am going to take a horizontal layer of fluid and just shake it up and down as hard as I can. And I'm going to increase the amplitude of shaking slowly and keep the frequency constant. Anyone care to guess what will happen? Well, first of all, nothing will happen. Okay? So as I increase the amplitude, nothing happens. Okay, there's a little surface waves, and then I get a sudden increase of surface wave activity. And if I do this right, I see we have a bit of a leveling problem. If I do this right, I should be able to get a square pattern here. Well, let's get you up and I can do that. Oh, it's because I'm not able to go slow. to get a disordered square pattern.
Close to.
Let me try higher frequency, that's all. Oh, I know what it is. It's the edge. I'm getting trouble from the edge. I overfilled my cell.
Too much water?
Yeah, I gotta turn my F down a little. Okay, well, I have a backup picture. Okay, maybe you can see that it's square. This isn't very convincing at all, is it? You buy it?
Kind of pushing the water up.
Yeah, maybe my patented method of moving through the water. That was a rag.
Paper towel. Right?
Okay, that may be the way to breathe. It depends on the depth.
If it's not deep enough,
Yeah, the bottom friction goes up. Every time.
it's easy to add water.
Oh, okay. Let's look at it.
Change your...
Okay, well, I'm not getting a very stable square pattern, and I'll show you the picture that I took. I got another fluid, which I'll go through in a second. Here's a picture of a fairly stable square pattern.
That's what we're aiming for.
Yeah, I can't get the, it only happens in a narrow range, okay?
But you add a bit more water.
Well, I think now I've got too little water.
That's what I mean. You can add a bit. But I think it's the level, no?
Yeah, actually, I want to go to my other fluid, which is more, it just does something else in a second. Anyway, so what's going on here? Well, it turns out that the surface of a fluid will support capillary waves, short wavelength waves, which will happily go along, dissipate down, and disappear. But if you take the horizontal fluid and shake it up and down, what happens? Well, it's just as if you take a pendulum and move the point of support up and down. The pendulum picks up energy if it hits the resonance of the pendulum. In fact, at half the frequency of the pendulum. Right? So those waves are oscillating at half the frequency of the driving oscillation. And what they are is capillary waves, which are driven into finite amplitude by parametric instability. Now, you can see this. In fact, you've probably seen it all kinds of times. If you take a cup full of coffee in a styrofoam cup and you drag it across the tabletop, it will sort of buzz across the tabletop, sticking along. And if you pull it at just the right speed, you'll notice the surface of the coffee abruptly, becomes violently wavy. Okay, now this effect was actually discovered by Michael Faraday, and it's called Faraday instability as a result. And the story is, I'm not sure it's true, but it's a good story. The story is that Michael Faraday was sitting in a wagon in England somewhere, and of course being England it was pouring, and in the back of the wagon with him were a bunch of barrels of beer, wooden barrels, and the rain had collected in a thin layer on the top of the barrels. And Faraday noticed that as you went across the cobblestones, you got a very sudden increase in the wave action on the top of these barrels. And because he used Michael Faraday, he noticed that the oscillation frequency of the waves was half that of the function over the cobble. And he immediately, went to the Royal Society and, that afternoon wrote a paper about it or something like that. Okay, so in fact, the Faraday instability, surprising as it may sound, produces all of the patterns that we just saw in the convection experiment, even though it's completely unrelated. And if my luck is with me, I will now attempt to make a stripe pattern. And it turns out that the parameter that's important is the viscosity of the fluid. So I will now sop up my water. I'll use a common fluid, at least it's common in my house, which is Johnson's baby oil. Actually, this is a terrible rag. baby oil isn't very viscous. You can do it with more viscous fluids, but the more viscosity you have, the higher the acceleration that you need is, and the more powerful a shaker you have to have. And so it turns out for a viscosity somewhere around that of pump oil, 50 Gs is not enough to produce the oscillation. So that's why you need a shaker with very high power. Okay, here's the baby oil. That's the chase here. Okay, now the frequency had better come down. And you notice it's not oscillating as it was before. I just had to find the answer. There we are. Oh, this one is pretty square. Whoa. Well, that's the beauty of demonstrations. You never do what you want them to do.
Some theories here. Somebody has a theory in his back.
Actually, I rather suspect it's because I've got some water in my
He had a water underneath. So it's getting linear.
Oh, now we're going to get some squares. Okay. This is actually a different brand of baby oil. It's obviously less viscous baby oil. Don't buy this. All right, so we're going to see our squares. This will probably come down. Let me go up to
But
frequency.
it's linear on the right.
Well, that's an effect of the light. Not the linear. Okay, let's go up to frequency and see if we can drive it there. You see, I shouldn't be able to drive it with frequency because it's not the expected. Ah, there we are. Now we got a bubble.
What a beautiful square.
Yeah, we do. All right. Oh, yes.
This is better water than the other water.
Yeah. All right, so these things look like rolls, but they're actually squares because the light is just winking off of one of the two. Okay, so we're going to get a nice square pattern except for that bubble. Get that bubble over there. Okay, now the nice thing about this system is that the time scales are very fast, which means that I can increase the control parameter and get new chaotic state, which is driven by the proliferation of a different kind of defect which happens in square patterns. And somewhere up here, it'll become quite unsteady. And then a little bit farther, it'll become totally chaotic. In fact, it's very difficult to follow. Very difficult to follow it because okay. It's difficult to follow because we're looking at it with a video camera, right? And the frequency of the oscillation is comparable to the frame rate of the video camera. And so when you get into these very fast moving things, you can't really see it with a video camera. In fact, what we'll do is we'll turn this off, and maybe after the talk with a little bit of fun, you can look at it. Okay, so what I tried to show you there, here by the way is a roll pattern. This uses pump oil, which is much thicker. So you get the straight ripples instead of the square. And you can also get much more exotic things, and this will appeal to some in the audience. If you make the layer very thick and shake it very hard, you actually get quasi-crystalline patterns. And if you know what a quasi-crystal is, it's a pattern with in this case, let's see, one of them is 10-fold periodic, this one, and the other one is 8-fold. In other words, you rotate it 1/8 and you get a pattern back again. And those are crystal patterns which were thought to be forbidden for a long time. But in fact, they've been discovered in solid materials, and now these are non-equilibrium patterns which have quasi-crystalline symmetry. So they're very exotic looking patterns. So here the top one is roughly square, this is roughly hexagons over there. This one is 8-fold quasi-periodic, and that one is 10-fold. These are experimental pictures. And they were taken by a group from I know. Okay, well, what about sand? You saw me playing with the sand at the beginning. Well, here's a shocker for you. Almost everything that I've told you about fluids, those patterns that occur in the shaking fluids and the convecting fluids, also occur in completely dry materials. If you take the same shaker here, and you make a little cell on the top, totally dry, pump the air out, and pour a layer of sand in there, and the layer has to be several grains deep, like maybe 10 or so, and you shake it up and down, what do you expect to happen? Well, nothing, and that's what you see initially, but as you keep going, there's an instability where the sand heaps up. And in fact, the sand sort of sloshes back and forth into little heaps, rather like the way the fluid operates, but it's completely dry. And it produces amazingly regular patterns. And these experiments were done, again, at the University of Texas at Austin, Harry Sweeney's group. Paul Uppenhauer, I think, did this one. And here's a regular square pattern. Every little white area in this pattern is a little heap of sand, actually little brass balls. And every dark area is a layer, a place where the sand is relatively thin or not there at all. Okay, now as you vary the parameters, you let air in or not, you change the frequency, you change the depth, and you turn it up, right? What happens is you get a whole bestiary of patterns, and what do you know? They all look like the patterns you've already seen. They're hexagons, they're squares. If you'd showed me this pattern up here a few years ago, I would have sworn that was a convection pattern, but it's in fact little heaps of sand jumping up and down on a plate. Okay, so now you begin to wonder, well, maybe this stuff is fairly universal, and uh-oh, what happens if you change the parameters a bit more? You see this, that's spiral defect chaos. That's the pattern that I showed you in convection at the beginning of the talk, and here it is happening in a bouncing layer of sand. Okay, so there's something about these patterns which doesn't even depend on there being fluid mechanics. Okay, and just to mention one more thing, and well, let me skip that thing, that's not so important. Okay, one of the things that sand does that fluids don't do, which is kind of interesting, is, of course, I'm probably not going to find the other thing that's described. Is segregate. Let me just explain it verbally. Segregation, you know, if you take a can of mixed nuts, you do this all the time in the bar, right? You take a can of mixed nuts and you shake it up and down, like I was just shaking that sand there, and you open up the can and look in, you'll find that the nuts have not mixed. They've in fact unmixed. And this is a characteristic of granular materials, completely dry, of different sizes. If you agitate them in a way that you would expect them to mix, they will often do exactly the opposite of what you expect. They will unmix. The big ones actually are carried to the top of the small ones, and they get stuck up there. So the big ones kind of float on the top of the small ones. And this is even true if the big ones are much more dense than the small ones. You can take a ball bearing made of steel and put it in a box of sand, which is much less density, bury it at the bottom, shake the box up and down, and open it up and look at it, the ball will be on the top. Okay, now this is a real problem in industry where they want to control the mixtures of grains. Every time you mix some grains, you want them to stay mixed, and you shake it around in the box, well, you know, they unmix. Okay, so this actually happens in a spectacular fashion in a little experiment which I also brought with me. Can I get some lights up? Sorry, I have to fiddle with my clock here. Now, let's see. So what I have in front of me here is a tube. And the tube is about half full with a mixture of table salt, which is white, hopefully, and hobby sand, which you buy at the hobby store, which is black. And you see that the sand in the tube looks sort of gray. I won't move back because we need to check that. And I mixed them up very carefully and placed them in the tube in such a way that they were stayed as mixed as possible, and that's actually kind of tricky to do. And now I'm rotating the tube at a frequency which is such that the sand streams continuously down the front of the pile. Okay, so it goes around the tube and it pours down, it goes around the tube and it pours down. Now the remarkable thing is that every time sand pours down the front of this pile, there is a process which has a tendency to sort it. And so after a few minutes, you'll notice maybe that the tube begins to develop some areas that are a little darker than others. And as you watch, it will in fact sort itself completely into bands of black, white, black, white, black, white down the length of the tube. Okay, and the reason for this, it took a long time to understand, and in fact it's quite controversial why this happens now. But I can give you a rough explanation as follows. One of the important things about big grains that's different than small grains, and that is that as they bounce down a complicated flow, there are fewer little gaps between the grains for them to get stuck in. Well, so the grains are bouncing down the front slope of this slope here, and if it's a small one, it has a tendency to fall in every little hole that it bounces across and get stuck there for a short time before it's knocked out. The big ones, on the other hand, go merrily bouncing down the flow and get to the bottom more quickly because they get stuck less often. Okay? So what we say is that for a given slope angle, the big grains have a higher downslope mobility than the small grains do. So for a given slope angle, the downslope flow of big grains is bigger than it is for small grains. And this actually happens in avalanches. The big guys come down and crush you before all the small stuff comes down and buries you, okay? Now, a consequence of that fact is if I turn the tube at a particular rate, then the angle at which the slope streams actually depends on whether it's big grains or small grains. If it's big ones which stream quickly, then the slope is more shallow than it is if they stream. I think I have it overhead. Yeah, I must do it. Oh yeah, here. Okay, so the downslope mobility of the big grains is larger than the small grains. So that means that as I turn the tube, if there are more big ones, the slope of the flowing surface is smaller than if there are more small ones. And you can sort of see intuitively why that might be true. Okay, now what happens if I look at the long axis of the tube? If there's a little bit of variation in the slope down the axis of the tube, what does that mean? Well, that means there are axial gradients. There are gradients that point down the axis of the tube. And relative, now this is tricky, relative to the average grain, the big ones move down those gradients and the small ones move up. Everybody goes flowing down the hill. It's just that the big ones go down faster than the small ones do. So relative to the average flow, the big ones go down the hills and the small ones go up. Now look, that's unstable because the bottoms of the hills, like in this little valley here, are where the big ones are going to pile up. And that's exactly the ones that prefer the lower slope. So if I make a fluctuation in the slope, where it's low, let's say this point here, then it will collect white ones, it will collect big ones, which are exactly the ones you need to amplify that depression in the slope. So the surface is unstable. As the thing rotates, fluctuations in the slope have a tendency to grow. And if you look at the tube now, you see that it's starting to show this bend. Okay, now it was thought for a long time that these bands were the result of a kind of irreversible diffusion process. And here's a little argument for why that's so. If you think about a drift velocity proportional to the axial derivative of the slope angle, okay, then you get something, if the slope angle is coupled to the concentration C, then you get a current which is proportional to Tc dz with a positive coefficient. Opposing that is the tendency of concentration fluctuations to be diffused away because the flow is very random, so you expect normal diffusion to occur. And so that gives you a diffusion-like term, a same sort of term, but with the opposite sign. So you've got a current that wants to sort them and a current that wants to mix them. And if you put those two currents into the continuity equation, you get a diffusion equation with a diffusion constant that can become negative. And if the diffusion constant becomes negative, then the system spontaneously unmixes itself. Okay, so it was long believed that this sorting process had to be basically diffusive. However, it turns out in some mixtures that it is not diffusive. Here's a picture of a space-time picture. Time is running downward, and space is the axis, the length of the tube is across the top. If you mix up the grains, take a video image every so often and assemble the video images into a vertical picture like this, and look at it, you see that there are traveling structures in here. You see these little white stripes that travel along like this? So the experiment that we did was to take that mixture and load the tube with little stripes that were pre-segregated. In other words, we loaded the tube with little stripes, black, white, black, white, black, white. And then we perform the experiment and see where those stripes moved or how they moved. And sure enough, you find that before you get to the later stages where the bands are saturated and stable, like these ones are, there's a transient regime in which the bands merrily travel along, like little traveling waves. Okay, now it turns out, in fact, that the dynamics of these concentrations in this supposedly completely diffusive kind of random-looking mixing flow are just as complicated as those of nonlinear water waves or something. They can pass right through each other, they can travel, and they can eventually saturate into these stationary bands. Okay. Well, I've shown you a lot of things. I've shown you lots and lots of pictures and videos and demonstrations and so on. Let me sort of begin to try to tie it all together. The whole subject of pattern formation is interesting in part because it really doesn't matter that much what the underlying instability is, what the physics of it is. It turns out that many instabilities with the same kind of nonlinear behavior give you the same patterns even though the underlying physics is quite different. Shaken fluid, shaken sand, shaken convecting fluid. All these things produce dynamics which can be understood in a kind of generalized way. So the ones that are marked in red here, I showed you some pictures of. All the green ones are other things that people in this field have studied. In particular, you see a lot of these kind of patterns in biology, the spots on the stripes on zebras and the spots on leopards and the things on tigers and so on are all thought to be driven by a kind of chemical organizational system which gives you different coats on different animals. You can look at chemical reactions, you can look at flames, cracks, dendrites, you can look at various electrical problems, geological phenomena. All of these things have mathematical similarities and they all produce non-equilibrium patterns. And there are lots and lots of experiments to be done on many, many different systems. So I call this other beasts in the zoo. If you're interested in seeing more or learning a little more about these things, please feel free to contact me. There's my website that Bela mentioned at the beginning of the talk, and there's my email address. And I want to give a free plug to a new book that just came out, because the guy who wrote the book is a friend of mine, who used some of my pictures. It's called The Self-Made Tapestry, and it's by Philip Ball. It is, as far as I know, the only popular book which actually collects together some of these types of phenomena and tries to give some explanation of it. And I will also mention quite bluntly that I'm very interested in any students who are interested in working on this type of a future. In fact, both this experiment and that experiment are eligible for sort of summer student funding if you want to work on these things in the summer. And I'd like to thank you for your attention.
Any questions? Just on that.
Your last time you showed us this regarding the strikes, you had the plot of function of time and the line.
Yeah.
That reminds me of the patterns that they see in cellular phenomena.
Yeah.
Streamers.
Yeah. In fact,
Some local rules that operate in the time. Is that what's going on in the line on that? Some basic nonlinearity operating locally.
yes, it is a basic nonlinearity operating locally. There have been a number of cellular automaton models of this process, and some of them are fairly realistic in the sense that you take a white grain, say, and you advance it down the grid at some speed, or you maybe go left or right randomly, and you have different behavior when it bangs into a black one and so on. And you can reproduce all of these things. Those tend to produce the diffusive dynamics, though. And the reason is that you don't get the oscillatory dynamics unless you have at least two variables which are both first order in time. See, if you look at just the diffusion of, say, the concentration, that gives you a differential equation which is first order in time, right? That cannot have waves. It doesn't matter what you do, it can't have waves. No matter how nonlinear you make that thing, it can't have waves. So that was the mystery. How can something that is just a concentration effect, be first order, be second order in time? It turns out that the second variable, and there's now a fairly elaborate theory on this by Igor Aronson and Lev Simmering from San Diego. It turns out that if you write a second equation for the slope, the local slope angle, separate from the concentration, and you write down two diffusive-like nonlinear equations, which are both first order in time, then you get wave-like motion. So both of those equations are local in the sense that they, each point only looks at the neighboring point. And they could both be incorporated into a cellular automaton, but it would have to be a two-variable cellular automaton, not a single variable. All the single variable, all the concentration-based theories of this fail because you can't get second-order dynamics. Yeah?
At the beginning you mentioned symmetry breaking.
Yeah.
Would you say that that's the biggest mechanism feeding all these patterns?
Yeah, in a very general, symmetry breaking is a pretty general concept. But yeah, all these things are symmetry breaking instability. That's the bottom line.
And I guess that's why when you did the experiment there with the water and the baby oil, they had the same symmetry basically, whether you had water or oil. It was
Yeah, that's right.
similarly symmetric. So as you saw squares with the oil is one.
Well, in fact, you can also get hexagonal patterns and stripe patterns, but all of those things will break the circular symmetry. I should mention, why do you get squares in some cases and rolls or hexagons? And roughly the way to understand that is that each of these patterns is essentially a stripe pattern. Okay? In other words, it has one wavelength and some orientation. And in fact, because of the rotational symmetry of all these systems, it in some sense doesn't care what the direction that the pattern comes up in is. Now, to get hexagons, or to get squares, what you have to have is a nonlinearity. In other words, a phenomenon that doesn't occur until the waves or whatever they are have grown up to some size, which makes those waves unstable to a stripe pattern of a certain orientation. So what happens in the square patterns is the stripe pattern will begin to grow, and it will immediately drive instability for a perpendicular stripe pattern. And those two things will reinforce each other and grow together, and that will give you a square pattern. Now, to get hexagons, you need three waves. Okay, each at 120 degrees to each other, superposed, and that gives you the hexagon structure. Now, if you superpose 5 waves, you get the tenfold quasi-crystalline pattern, and so on. So the question of whether you get squares or stripes or rolls hinges crucially on the exact nature of the nonlinear interactions between waves with the same wavelength but different directions. Okay, so that's, if you change the viscosity of the fluid increase the viscosity of fluid, it turns out that the coupling between this wave and that one is suppressed, and then it goes back to just a stripe. And all those nonlinear behaviors are dependent on how hard you drive the system. And so it's the disappearance of those nonlinearities that give you the transition, say, between squares and stripes, or between hexagons and rolls. Those are all buried in the rather hard to understand nonlinear features of the problem.
In your sand experiment, these mountains of sand, there was no motion of it was a stationary picture you had of valleys and edges.
Oh, in the shaken sand?
Right.
No, it's not stationary, actually. The picture is a snapshot.
Okay, so snapshot, so the thing was moving like a wave, or was it the...
You mean the Texas sand experiment? The one with the little squares.
Well, you have the squares, you also have stripes of sand.
There.
Right, like the upper right one.
Right.
Was it
No, it's not, well, the stripes are sort of stationary, but on the next half cycle of the drive, everything that's black in that picture will be white.
Okay, so it's going up and down.
That's right. It's sort of sloshing like this.
Okay.
It's in that sense, it's closer to the shaken fluid experiment than convection. The shaken fluid experiment, the fluid sloshes back and forth in these little waves. In the shaken sand experiment, the sand kind of, in some sense, sloshes in a similar way.
So every other picture, it goes black and white, black and white, black and white.
Yeah, but these are different patterns. If you look at this one, it has a different symmetry than that one.
Sure, but still the thing about something growing up and then going down, going up and going down.
In fact, in this picture, you see the coexistence between sort of black-centered things and white-centered things. Those are things that differ by 1/2 period in the drive. So it's a subharmonic. In other words, it goes at half the frequency of the drive. Yeah.
Well, thank you, Steve, and we can keep on discussing this and coming here, and next door there are some donuts and coffee. Thank you all. You had a whole bunch of bonds at the end. They had to go somewhere.
I'm hearing period doubling.
It's not a real low frequency. It's like splashing.
Ça va aller. La pression orale, 15 minutes. Pas de force. OK. OK. Évidemment, j'imagine que les thèmes sont assez divers. Les sujets sont très... C'est ça. Est-ce qu'il fait une présentation orale pour la classe ou un post?
At low frequency, you can also get hexagons.
J'ai plus de confirmation encore.
Non, non.
Next to it is square. Try lower. Okay, if you're a true believer, and you go over here and you look straight down, you'll see that it's formed a few hexagons in the middle.
Amen.
There's a little bit after. You look in, you see the Virgin Mary's face. Anyway, if you go down to low frequency, there's another thing comes in and you get hexagons.
Actually changes from hexagon.
Well, this is probably kind of a mess of hexagons and squares. Plus, we're at a frequency for which the video camera is really not good. So, just looking at it.
pattern?
Well, it's obviously not. The problem is that the sidewalls also launch waves, and if you do it correctly, yeah, I think I have some now.
Oh, yeah. A nice two hexagons in the middle there. Very nice.
Are there any set of parameters where you have two coexisting
Yeah.
equal energy?
Yeah, a lot.
And you split them one to the other?
Well, you can see them more clearly if you look at it with your eye and on the screen, as they're wiggling around. Oh, yeah. I don't know why the video image just doesn't really look like what your eyes see at all. Yeah, well, it's 30 frames per second interlace. That's a big problem. Interlace. It depends on the temperature because the temperature is dependent viscosity is on.
But the vibration boost temperature is part of the energy you go out.
Yeah, that's right. It warms up. Yeah, it warms up from viscosity.
And also the lamp.
Yeah. Well, I mean, this is a hard problem because it's really hard to temperature control under a free surface, right?
Right.
And in fact, most of the dissipation, because of the rigid boundary condition on the flow at the plate, almost all of, the flow is up near the free surface. And that means that all the dissipation is up there too. So the fluid will actually become stratified and hot on the top. And then these properties drift with the temperature, and so it's, people have learned how to fix all these things. In fact, they use infrared lamps to do temperature control. Yeah, I actually have a non-interlace video camera, but I haven't implemented that yet. Okay, well, I better pack up and Can I get donuts for a while and then pack up? Whew, I think I didn't bring the, well, I got a little more here, okay. I didn't bring the cooling gas. All right, let's just come back. Oh, okay. It would have come in by now.
Yeah.
Well, this was the teasing run. Next time it'll be better.